Welcome, lesson 3-14. Today, before we get going, the first thing I want you to do, because we're going to be looking at constructing graphs of polar functions, I have created something on Desmos I want you to use. What I want you to do is go to your Google Classroom. Once you log in, I want you to go to your classwork, find Unit 3, scroll down to Unit 3. This is lesson 3-14. Find that, and within there, you'll see an attachment that says Polar Graphs Desmos. I want you to click that open. We're going to use that today. Make sure you have that graph going. I'll let you pause your video to get there. It should load with something similar to mine. Make sure you have this graph open. We will use this all throughout today's class period to really help us out. So go ahead and do that now. Make sure you go to Google Classroom, 3-14. You'll see a Polar Graphs attachment. Hopefully that was enough time for everybody to get to this graph. Again, it was Google Classroom, 3-14 is the folder. You look for Polar Graphs, bar, Desmos, you click it, it opens up this. Let me explain what you're looking at. Last class we did polar function or polar graphs, and we also did rectangular graphs. This is the same way. On the left side, notice the title in blue, it says polar graphs of a function. On the right, it's going to be the rectangular. Last class, we only did points. Today, we're dealing with a whole graph. How the point system worked. Do you remember on rectangular how I said it was a locked system? What did I mean by locked system?
Yeah.
Doesn't move. The y-axis over here, it's positive when you go up, it's negative when you go down. That never changes. For the x-axis, it's positive when you go right, it's negative when you go left. X is negative when you go left. Okay, the polar system was not locked. Do you remember what it was that changed?
The axis.
The polar axis. Okay, so let me show you the first thing, how this graph works. Take this slider on the left side. Take your slider. As you start to move it, you'll notice something changes on the polar graph that does not change on the rectangular graph. On the polar graph, you'll see this gray line rotating. That represents the polar axis spinning. Does that make sense to you? On the rectangular, it doesn't change because it's locked in place. The graph sure moves, but the polar axis moves, it rotates on the left graph. On the right, you won't see any axes moving. That's the first thing I want you to notice. And the second is this. Do these two graphs look exactly the same? Believe it or not, they're the same equation. But in polar, they look quite a bit different than they do in rectangular. In rectangular, this is just a good old-fashioned wave. In polar, you're going to learn this is called a limacon. It's a French word. I'm going to call it limacon today. That's a limacon. But here's what I want you to notice. When I graph a polar function, I'm going to move this to, it's easier if you look on the top. I'm going to track it to pi over 4. I'm going to move my point to where this tracks to pi over 4. You see this gray axis right here? My graph, the point of purple, will represent where the graph is at any point in time. Has to be on that axis, which means if it was a positive value, it would be towards pi over 4. Don't remember this from last class? Positive is when you go towards the angle. Negative is when you go away from it. Is this purple point in the place of a positive R value or a negative R value if it's away from the angle? It's negative. And you can see over here, it's a negative 0.8. Now I'm going to track it along, and I'm going to go now to 7 pi over 12. I tracked it up to 7 pi over 12. Now, here's my purple point. What would you tell me about my purple point? Is it a positive R value or negative R value? Positive. Why is it positive? It's going towards the angle. Now, how does that compare with rectangular? Well, it would be if it's above the x-axis or below. You see how this is, we said it was positive? It's positive because this is above the x-axis. Okay, last thing I'm going to show you before we get into it. What happens when I'm at a 0 on a rectangular graph? Let's see how that compares on a polar graph. What happens when I'm at a 0? Here it is. I'm at a 0 on the rectangular. How does that correspond on the polar? It's the origin. Very good. That's a very big key thing today. Anytime we hit the x-axis on a rectangular graph, that corresponds to hitting the origin on the polar graph. They call it the pole. It hits the pole whenever you hit a 0. So a 0 becomes an intersection with the pole. Make sense? Okay, hopefully you catch that today. This maximum value, how tall is it over here? 6. This is a maximum value of 6, but here, look, it's not the same height. Do you know why? This 6 is still considered 6. It's because in polar, you don't go up and down, you don't go left and right, you rotate and you look at the largest value from the pole. It happens at pi. You see how that's at pi right here? At pi, this would be the maximum. Guess how many circles this is out? If this is up at 6, guess how many circles this is over here? Well, it's zoomed a little different. This is the circle 5. This would be at 6. What I'm trying to say is it's at 6. You can look over here, it'll tell you. That's at a value of 6. So with that, we're going to get started. That's your introduction. Let's go over to your note packet now. Now, today's lesson, as we start example 1, could be extremely long if I review you on everything. So I don't want to review you on everything. I'm just going to talk through it, and if you forget, hopefully at some point in time it'll click and be like, oh yeah, I remember now. What we're going to first look at is example 1. We're going to graph r equals 4 sine theta. So go to your calculator, go to your Desmos. I want you to type in over here on the equation, it says f of theta equals, just change the 2 minus 4 cosine, make it say 4, I've already forgotten. What was my equation? 4 sine theta. Sine and the theta button, if you just type in THETA, it'll change it to a theta. There I have it written. THETA, it'll go to a theta, or you can pull up your Desmos keyboard, press the ABC button, and you'll find theta under P. My question for you is this: 4 sine theta, what shape does it look like? Look. I can't talk. What does it appear to be?
A circle.
It's a circle. Good. What's the maximum value away from the pole? Like, what's its highest point away from the pole? How many units is that, or how many circles is that?
2.
If you're never sure, just look over here where it says R. 4 units away. Come over to rectangular graph. How far away? What's the maximum height? 4. Good. This is a circle pointing up. Before I get started, any guesses why it's going up? It goes up to 4 because the number 4. Any ideas why it goes up though? Emily has it. What are you saying? Sine. Sine is what letter? Y. What do you think would happen if I put a negative in front of the 4? It would go down. Good. What if I change it to a cosine? What do you think will be different now?
It's going to be the x value.
It'll either go left or it'll go right. Okay, y'all are catching on. Good. We're looking at 4 sine theta. So 4 sine theta, we should have a circle that goes up to 4. So back over here, we're going to get a circle that goes up 4. Let me show you how it happens. What I would do if I were taking a whole lot of time is I would remind you of how you plug in values. I'm just going to go really fast. I'd plug in a 0 first. That's the theta, plug it in there. So I'd be solving for the value 4 sine theta. Not sine theta, sine of 0. If you remember, sine on a unit circle, the sine starts at its maximum, its minimum, or its midline. It starts at the midline. The midline value for sine and cosine is the square root of 0 divided by 2. That's the midline. Now, you might be saying, whoa, wait, why is that? Today I don't have the time to talk about it. You could do your hand trick and figure it out. I'm just going to go fast. This right here would reduce 4 times, that'll be ultimately times 0 divided by 2. It's going to equal 0. Go to your graph, and at theta, put the point at 0. That would be your very first point. When our our polar axis is at 0, we would have a value of 0. Remember, this is the positive side, this is the negative side. Okay, the next value you plug in is pi over 6. If you remember from sine and cosine, they are waves that follow a consistent curve, which means there was a pattern. If this previous one was 4 square roots of 0 over 2, this one will be 4 square root 1 over 2. Which, when you reduce it, is going to be the value of 2. Now, you don't stress over that today. So here's what would happen. This is pi over 6. Your rotating axis would go to pi over 6. Where would 2 be located? Would it be towards pi over 6 or away from pi over 6? Towards it. So go 2 circles, put a dot. That's our second point. The next value, I'd plug in pi over 4. It would simplify to be this, 4 square root 2 over 2. Notice the pattern. Remember, sine and cosine, they count up the square roots. And this would reduce to become 2 square roots of 2. I believe 2 square roots of 2 is something like 2.8. I think it's 2.82. So let's go to pi over 4. Put your next dot at 2.82, wherever you think that would be. 2.82 is somewhere in there. Okay, I'm going to continue on. Again, if I go too slow here, we're never going to make it. The next one by pattern, just go by pattern. It should be the square root of what number?
3.
Square root 3 over 2. This reduces to become 2 square roots of 3, which I think is 3.46. So when we go to pi over 3, place your next dot at 3.46. Do I go towards pi over 3 or away from it? Towards. 1, 2, 3, 4. So it's right in here somewhere, 3.46. Finally, I get to pi over 2. If you remember your unit circle, this is where sine achieves its maximum. So it'll be square root 4 over 2. That's the maximum. This value would reduce to be 1. Sine's maximum when reduced is 1. So it's 4 times 1. What is 4 times 1? 4. So at pi over 2, you're at the fourth circle. So at pi over 2, 1, 2, 3, 4, you go up to the fourth circle. And we've now completed half of our circle. Okay, so now let's do the other half. The other half begins at 2 pi over 3. When I'm at 2 pi over 3, by pattern, your square roots count up till they get to the maximum, and then they start to count down. So this would be 4 square root 3 over 2. I'm now going to start counting down. We've already had that value. That value reduced to be 2 square roots of 3, which is approximately 3.46. Go to the 3.5 circle. 1, 2, 3. 0.46 is somewhere in there. Next point, I'm going to keep rotating my axis, is 3 pi over 4. 3 pi over 4 would be 4 square roots of 2 over 2. Again, you could do your hand trick later, but I'm just going faster here. This value we already have written right there. That's going to be 2 square roots of 2, which I told you is approximately 2.82. 2.82. Wherever you think that is, plot that point. We have almost completed our circle. I go to 5 pi over 6. This would be 4 square root 1 over 2, which again, I have that value written right there. It reduced to become a 2. Don't stress on the table. I'm just trying to walk you through methodically how the graph would look. So go 2 units towards 5 pi over 6, put that point. And when we come to pi, we complete our circle. This is 4 square root 0 over 2. That value is written right here. That reduces to be 0. 0 in a polar graph means you are back at the pole. So by the time I get to pi, I've completed the whole circle. So you could go ahead and connect your dots. I'm going to use a little tool because I can't draw to save my life. So I'm going to cheat. There's a little tool. There's my circle. Cool how that worked? I'm going to show you a faster way to graph in a little bit. That's why I say don't stress on the table. But this is me methodically showing you how it worked. Now, what happens on the lower half of the graph? Do you think we're going to have a second graph down here? A second circle? No, we're not. And let's find out why. When I go to find out 7 pi over 6's value, look what happens. When I go to, remember how the square roots work. They count up to 4, and then they start counting down. And I got to 0. You don't stop counting down until you get to -4. So now I'm going to have the negative square root of 1 over 2. So when I reduce this one, it's the same mathematical value of 2, except I have a negative in there. So now it's going to be -2. Here's my question. What do you do with a negative value when you graph polar? You go away from the angle. So instead of moving towards 7 pi over 6, it goes 2 away. And what do you notice about this point? It overlaps. What do you think is going to happen at every single value as we continue on? They'll just keep overlapping. So I'm going to go ahead and place this. If you want to fill in your table, go ahead. I don't want to use too much time there, but these values would overlap. So I'm just going to, if this is -2, it corresponds to this value right here. What's the next value going to be on this spot? -2 square roots of 2. What will the next value after that be? -2 square roots of 3. How about the next one? -4. How about the next one? How about the next one? And finally, -2. Good. If I included a 2 pi? If I included a 2 pi in there? 2 pi would be 0 if you wanted 2 pi on your table as well. You could add that in. 2 pi would be 0, and that all it does is it relapse over. So you wouldn't actually see it. Technically, it's two circles sitting right on top of each other. You don't see them, but there's actually two circles. The name of this polar curve, I just said it. What do you think we're going to name this polar curve? A circle. That's the name of it. Okay? So let's try part B without using Desmos this time. What do you think on 1B, -6 cosine, what do you think it's going to look like? It'll be a circle, but it's on the left. Why left? Why not down? Why not right? Why not
Because it's cosine and it's negative.
cosine and negative? Remember, sine and cosine, they have a maximum of 1 and a minimum of -1. Because it's cosine, it's an x value. So -6 times the positive 1 will give you -6. -6 times the -1 will give you, wait, did I say that right? -6 times cosine's maximum will be -6. -6 times cosine's minimum, which is -1, will give us +6. It will go from 6 to -6, but it'll overlap. So here's how this works this time. You plug in your points, and I'm going to go a whole lot quicker. -6 cosine of, you'd first plug in a 0. Cosine, think about the unit circle. Cosine, you start at 0 right here. Is that cosine's maximum, minimum, or midline? Maximum. Cosine's maximum is 1. What's -6 times 1? It'll be -6. So when we have a 0 value, we have -6. Where would I plot -6? Away from the right. So 6 to the left. 1, 2, 3, 4, 5, 6. Plot that point right there. The next value, again, you could do, if there's the same square roots, you could do the same pattern. I'm going faster. This time, what happens to my x value when I go to pi over 6? It gets smaller, so it'll have that square root of 3 value. I think, you know what, maybe I should write it out the very first time. I forget here, just to make sure I don't make a mistake. This would be -6 times the square root of 4 over 2. Cosine starts at its maximum. And we said that is -6. The next value would be -6 times the square root of 3 over 2. And so that would reduce to be -3 square root 3. Now, I don't know what that value is. Let's go find out what that is in calculator. -3 square root 3. What? SQRT. -3 square root 3 is -5.2 approximately. So let's go to -5.2. So I move my polar axis to pi over 6. We're going to be at -5.2. Where do I go for -5.2?
To the,
Up and to the right or down and to the left? Down and to the left. 1, 2, 3, 4, 5. Add a little extra. -5.2 right there. Okay, next value. This would be -6 square root 2 over 2. And I'm realizing I don't know a lot of these square roots. That's -3 square root 2. I don't know what that is. I'm going to check that one. This will be the last one I have to check, and after that we can roll through it fast. I'm getting -4.24. -4.24. So let me change my axes. My polar axis, I should say, it's singular. To pi over 4, -4.24. So do I go towards the angle or away? Oh, wait, 1, 2, 3, 4, and a little bit more. It should be right there, 4.24. The next value, -6 square root 1 over 2. That becomes a 1/2. -6 times 1/2 is -3. That's going to be an easy one. So at pi over 3, our R value is -3. Which way do I go for -3? Up and to the right or down and to the left? Down to the left. 1, 2, 3, right there. At pi over 2, cosine is going to be 0. Whoops, wrong color. It's the square root of 0 over 2, which reduces to be 0. -6 times 0 is 0. That means at pi over 2, the graph hits the pole, hits the origin. Right there. So we've completed half of the circle. The next values, I'm going to start going a little bit faster here. It'll be -6 Now it's the negative square root 1 over 2, which is just the opposite. It's the negative of this value, which means this time it's going to be of this one right here at the 1. It would become a positive 3. So when we get to 2 pi over 3, we should be at positive 3. What does it mean if you're at positive 3 at 2 pi over 3?
Up and to the left.
Up and to the left towards the angle. So it should be right there, positive 3. At negative 3 at 3 pi over 4, we should have negative 6 times negative square root of 2 over 2. This is getting to be crazy math to say out loud. What value will that be? 3 square roots of 2. Does anybody remember what that was as a decimal? Was it 4.24? I think it was 4.24.
Yeah.
1, 2, 3, 4, and a little bit extra. Let's plot it there. Okay, I'm going to start filling these in faster. Well, I'll finish the first cycle. So negative 6 times the negative square root of 3 over 2. That reduces to become 3 square roots of 3. And that was, I think, 5.2. All these numbers I no longer am remembering. 5.2. 1, 2, 3, 4, 5, a little bit extra. And just like that, at pi, we should complete this value. What value should we get at pi? Will it be a positive number or a negative number? At pi, should we be moving towards pi or away from pi? Towards. We should get a positive number. The reason it's positive is because it's negative 6 times the negative square root of 4 over 2. Negative square root of 4 over 2 is negative 1. Negative 6 times negative 1 gives us the positive 6 value. From here, if you wanted to add in your circle, go for it. Just try to connect your dots as best you can to create a circle there. I'm going to... Oh no, I messed up. Let me try this again. I'm going to use my circle tool to help me out. There's my points. And so what would happen starting at 7 pi over 6? It starts overlapping, which means this time at 7 pi over 6, just tell me through visually. I'm going to make sure you're figuring this out. I have this over here so you can see it. At 7 pi over 6, would I get a positive value or a negative value? Look where the graph is intersecting this line. Would I get a positive value or a negative value? I'd get a positive value. That's right. I'd get a positive value. If you wrote it down, it's because it's a negative times a negative, which turns out to be positive. We already have that value written down. That is right there. You would get 3 square roots of 3. Let me go green. 3 square roots of 3. Which means the second, when you start overlapping, you'd have that point, and then you'd hit all of these as you go around this way. So it would go on this path. That's the path. You would start it on the left, and it would circle against the clock going this way. That's how the circle would be formed. So you could go through and fill all these out if you wanted to. There's your rest of your values. What's the name of this graph? A circle. This is once again a circle. Okay. Before I give you one to take a look at, I want to see if you can summarize some things I've said to you. On extra practice, it says, if a polar function can be written in this form, then the graph will be a circle. Can you describe by rule the direction of the circle? Could you tell me if it was going to be up or down, left or right? How would you know if it was going to be up or down?
If it was sine.
If sine would go up or down, what would make it go up versus down?
If it's negative.
If A is positive versus A negative. What does it mean if it's a cosine?
That is going left or right.
Left or right? What about A?
If it is positive, it's going to the right. If it's negative.
Okay. So what's the similarities between both graphs?
The A determines.
The A determines its maximum. They are all circles. What are some differences? If it's sine,
It's going
up and down. Cosine goes left and right. So could you predict the differences by looking at the graphs now? The equations, I mean? Could you predict the differences? Okay, finally. What are the polar coordinates of the point that is farthest away from the pole? How is it related to the equation? What I want you to know, the farthest away, the points that are farthest away is whenever either the sine or cosine achieves its maximum or minimum. When cosine itself either gets to be its maximum or minimum value, that's when you're farthest away from the pole. When is it farthest away from the pole? It's maximum or its minimum. Okay, with that, try DOL number 4. All right, example 2. So this is where I think some students will start to like this more because now you'll get to see, here's the quicker way of doing things. In my opinion, and it's the reason I designed my Desmos graph as I have, it's much easier to graph polar functions quicker if you first think of its rectangular graph. So reminder of pieces. When you look at an equation, if you're going to graph this polar is when it's r equals with a theta, I would use the rectangular form. I'm going to exchange r with a y. So the y value is equal to r. Go ahead and put that on here. The r value is equal to the y. The x value is equal to the theta. The theta will equal the x value. So I'm going to graph it. I want you to remember that the number that comes by itself is what we call the midline. The number that's all alone was the midline. So go to your graph, find 4 on the y-axis, and use your ID badge to draw, and I would recommend you use a dashed line for the midline all the way across. We got a little review here. If you don't remember, go back to lesson 3-4 and watch how to graph sine and cosine. The number in front of the cosine that's multiplying with it is what we call the amplitude. You may remember that. That was amplitude. That's how far the graph will go up and down from the midline. It's going to go 4 units up and 4 units down. Okay, question for you. Cosine. Which variable is cosine? X. So when I start at 0, is cosine at its maximum or its minimum or its midline? Cosine is x. When you start here, is there x value on the circle, on a unit circle? Is that the maximum, the minimum, or the midline for x? Max. Cosine's max is 1. So this will be 4 plus 4 times 1. What's 4 plus 4 times 1? 8. We'll begin at the maximum value, which is 8. Go over here, put a dot there. One more review question. What's the period for cosine? Perfect. The period for cosine is 2 pi, which means if you go 2 pi across, we'll have another point that's going to be at 8. You could look here in this circle. We start at the maximum at 0. We reattain the maximum at 2 pi. Okay, when will cosine achieve its minimum? Where does the minimum occur? At pi. At pi, go over here and go 4 units down from the midline. Are we good? Now, at the in-between values, that's when you actually hit the midline. So what's in between 0 and pi? Pi over 2. At pi over 2, we're going to have a midline value. And at 3 pi over 2. Now, all we're going to do is those 5 key points. We're going to graph using just those 5 key points. So on the last problem, it took forever because it was a table with all those values. I think it's much easier to use the rectangular. We're only going to use 5 values, and we're going to estimate the rest. So this, I start at 8, and by the way, what kind of shape does cosine look like? A wave. We're going to graph a wave. As best you can, graph a wave. Okay, so this is what you got to wrap your mind around when you go to graph, is how to translate it. But once you catch on, this will start to be a lot easier method. We're going to graph only the 5 key points. I'm going to start with my value of 8 at the angle of 0, which means I'm starting with my polar axis looking like an x-axis. We have a value of 8. Which way do I go if it's positive 8? Do I go to the right or to the left? To the right. 1, 2, 3, 4, 5, 6, 7, 8. What's the next key point we're going to see? Pi over 2. So go to pi over 2. And at pi over 2, what's our value? 4. So go, it's positive, so we go up 4. 1, 2, 3, 4. Put a point. Now, if you want, you can connect these two. They will be a curve, but it's going to connect from here to here. So I'm going to start to connect this as like a curve. And I'm a horrible artist, but I'm going to do the best I can. Everybody following so far? Okay, when I go all the way to pi, when I rotate to pi, as I go around, what's happening to my values as I approach pi? Well, what is my value at pi? 0. If it's a 0, that corresponds to hitting the origin. Now, don't flatline this. This was a curve, so it doesn't just hit there and make like this hard line like that. What happens to the graph is it was at 4 and it slowly decreases to 0, which means you could predict some values. Around 3 pi over 4, it looks like we're going to be a little bit greater than 1. So if you wanted to add another dot or two, go to 3 pi over 4, 3 pi over 4, and you know you're just a little bit bigger than 1. At 3 pi over 4, we're a little bit bigger than 1. It'll be somewhere in there. So this graph must look something like this. It's going to hit, and it's going to come curve through like that, and then hit the pole, which we call the origin. Okay, now what happens after pi is we're going to go to 3 pi over 2, which what's the value at 3 pi over 2? 4. So let me spin this axis. When I get to 3 pi over 2, I should be at 4. Does that mean I go up, down, left, or right? I go down. Positive is now down. So 1, 2, 3, and 4. Plot that dot. So one more time, this graph is going to go from this point, and these are all positive, so that means it's going to be going towards the angle. It's going to come around. It looks like I'm going to put the other pi over 4 point a little bit greater than 1. It looks like it's going to go and repeat the same thing, but it'll be symmetric on this side of the graph. All right, and then finally, my last point is 2 pi. What's the value at 2 pi? 8, and it's increasing the whole way, which means on this polar axis, as I rotate, it's constantly getting, larger and larger and larger as I rotate to 2 pi. Oh, man. Okay. It should constantly increase until it gets there. So it should keep getting bigger and bigger and bigger as it curves to that point. This right here takes the name of a cardioid. The reason it's a cardioid is because it's obvious in my picture. It looks like a heart. And cardio means heart. That obviously looks like a heart in my picture, correct? Okay, I was hoping y'all would say no. I was being sarcastic. It's supposed to look like a heart. I just can't draw to save my life. A heart. I said a car?
Yeah.
I don't know what I'm thinking about. It should look like a heart. And that's why we call it a cardioid. Cardio means heart. Cardioid is a mathematical object that looks like a heart. Let's go look at it in Desmos. The equation was 4 plus 4 cosine. You see how now it looks a little bit more like a heart? The thing it's missing is it's missing the point on this end. It's not pointed, it's rounded. But everything else looks like a heart. If you don't think it looks like much like a heart, change this to a negative sign. Change it to a negative sign, and you'll see it does look a little bit more like a heart. If I change it to 4 minus 4 sign, see, it looks a little bit more like a heart, doesn't it? What's wrong with y'all? I try to show y'all a cool lesson, and y'all you're like grumps. It doesn't look like a heart. Well, that's what they named it hundreds of years ago, and so it's sticking. You can't change the name. You're too late. Call it the cardioid, which means heart, because they think it looks like a heart. All right, hey, one more time. I want you to watch my polar axis. As my polar axis spins, notice where we're plotting points. You're always plotting the point on the axis. Does that make sense? So at 7 pi over 24, if you were just starting here on your own, you would say there's 3 potential places this point could be graphed. It could be here, here, or here. The way to determine is to keep tracking along, rotating to see which one would accurately follow and keep intersecting the graph in a constant pattern. Constant might not be the right word in math because constant means flat, but in the consistent pattern. And so there's only one way of tracking it. Okay, next question for you. How long does it take to complete the whole shape? On a circle, we could complete the whole shape in pi. Do I complete the whole shape in 1 pi? How long did it take to complete this whole shape? 2 pi. Here's the reason. It's because this graph is not perfectly reflected on the x-axis. If it perfectly reflects on the x-axis, oftentimes it only takes pi to perfectly graph. I don't know if that makes sense to you, but that's how it works. Is this graph over here on the rectangular version, was it reflected on the x-axis? It was going to take all 2 pi then to see the picture. Okay, let's go look at example 3b. Hopefully we can speed it up even more. Oh yeah, we're going to keep trying to speed it up. Tell me if your equation is r equals 2 minus 5 sine theta, and you had to graph it. The way I'd recommend it is for you to do a quick sketch of the rectangular version. What could you tell me is the midline of this problem? 2. Go ahead and note that. That's the midline. So on our graph, we're going to add in a dashed line at 2. That's our midline. Okay, what does the 5 represent? The amplitude. The amplitude is always listed as a positive number, so you'd say amplitude is 5, even though it says -5, you'd say the amplitude is 5. The negative means, for the sine values, you'll do the opposite. It'll just be a transformation. So sine, when we start here, is sine at its maximum? Wait, what letter is sine again? Y. Is sine at its maximum, minimum, or midline? We start at the midline. Put that dot. We start at the midline. And remind me, what's the period of sine? So go 2 pi away, place another dot on the midline. Now sine is supposed to start increasing first, but because of this negative, sine will not increase. What will it do instead? It'll decrease. So we should get the maximum at pi over 2. That means at pi over 2, we'll actually get the minimum. At pi over 2, go down 5 units. 1, 2, 3, 4, 5. So sine goes up to its maximum. Sine returns to its midline at pi. So at pi, we have another midline point. Sine achieves its minimum at 3 pi over 2. But because of this transformation, it's not a minimum. It becomes a maximum. So at 3 pi over 2, go up 5. 1, 2, 3, 4, 5. Again, this is lesson 3-4. If later you want to go watch that video again on how to graph. Connect those dots with a wave. And let's turn this into a polar graph. All right. Tell me, what will these zeros become? It'll become intersections with the pole. This graph is going to hit the pole and intersect with it. This graph will not be perfectly symmetrical, meaning, it won't overlap itself because below the x-axis, this part of the graph does not perfectly mirror what happens above the x-axis. So we're going to have a different looking shape this time. Let's start. When we start graphing at 0, remember the r is equal to the y value. R has been replaced by y. The theta is being replaced by the x, so this is going to be our theta. When we start here at 0, with the angle of 0, our r value is 2. So place a dot at 2 right there. Now, what's happening to our graph over here? Is it increasing or decreasing? Decreasing, which means we're going to get closer and closer to the pole. We're going to hit the pole somewhere before pi over 4. So we will hit the pole. I'm not sure exactly where it'll be. I'm just going to put a dot there. What's going to happen is this graph is going to decrease. Decrease means go closer to the pole. It's going to first decrease as we spin towards pi over 4 this way. This graph is going to decrease. So it's going to decrease and hit the pole. And it's going to hit the pole somewhere around pi over 4, maybe a little bit before. And then what's going to happen? It's going to go to pi over 2. By the time we get to pi over 2, what's our value? -3. Now, negative means go towards it or away from it? Away. So we need to go down 3 units. Down 3 units, 1, 2, 3. And to make sure you see how I should graph this, follow my axis. I'm going to take it back again. We started here, and I want you to think through where the point would be on the axis. It should be decreasing on this axis. Since this is decreasing, my point should keep decreasing down this axis as I rotate it. So it moves, moves, moves. At this point, I'm at the origin, and now it's going to keep decreasing more and more and more until it hits that point. That means it gets rounded this way. Does that make sense to you? From here, it's going to keep rounding until it hits that point. So it's going to round like this, where it's getting more and more negative like that. Now, from pi over 2, we're going to increase to pi, and at pi, what's our value going to be? 2. So whenever I rotate all the way around to pi, whoops, that's not what I want to do. By the time I get all the way to pi, my value should be at, not pole, but at 2. Which right now it looks like, wait, did it go like this? Did it hit that? No. I started negative and I started increasing. So let me turn it back and show you how this is going to work. So starting here, I start at negative values. And as I rotate, it's going to climb it this way to achieve that point. So follow the axis as I rotate it. It's going to climb these values to get to +2. There's +2. I'm at -3. It's going to climb up this way. So from here, as I rotate this, it's going to be moving this way, this way, this way as I spin it, which means it's going to have a 0 somewhere. I don't know how I drew that. It's going to go like this. It's going to come up and over this way to 2, like that. That's how it's going to work. Now, some of you have never seen these graphs before, so you have no idea what it should look like. I kind of have an advantage that I've done this a bunch of times. I have an idea how it's going to work. Okay, so now we're there. Now what's going to happen as we approach 3 pi over 2? My graph is going to keep increasing until I get to 7. At 3 pi over 2, I should have 7. So 1, 2, 3, 4, 5, 6, 7. Now I should keep increasing, which means I should be on this axis as it stands. Which way should I be moving on this axis? To the left or to the right? To the left. It's going to keep increasing. That means if I follow my axis as I spin it, I should keep going further and further this way as I spin it. So my graph is going to be getting longer and longer and longer like that. It's going to curve out that in that direction. So it would look like this. It's going to curve out and hit right there. And now finally from 3 pi over 2, my graph will increase or decrease? Decrease until we hit 2. So it's going to decrease. So my distance from the pole, which is the R value, is going to continue to decrease until I reach that point. And this was super ugly, so I'm going to try it again. It's going to continue to decrease until I reach that value. That right there is what we call a limacon. It's a French word. Limacon means snail. People think it looked like, when they named it, they thought it looked like a snail shell. If I flip it upside the other way, a lot of students see it, and I'll show you on Desmos here in a second. That's a limacon. I call it a limacon. And the way I encourage you to remember it, a lot of you know some Spanish roots. Con means with. It comes with an inner loop, with a loop. That's how I remember limacon. You do need to know the names. If I hadn't said that, that's the first. Cardioid is heart. Limacon comes with a lima loop. That's how I recommend you remember it. But it comes from that means snail in Latin. Let's come over. In French. Sorry, in French. Let's come over here and graph it. What was our equation again? 2 minus 5 sine x. There it is. That's what the graph looks like. I told you it's called a snail. If I flip it around the other way by making it a +5, You see how it kind of looks like a snail shell? Some people say it looks like Toad's head. If you're a Mario fan, it looks like Toad. Yeah, Toad is a snail. No, total lie. Not true. Okay. Again, you could follow on the graph and you can see how we got our points. It's easier on this to see how with the rotating axis, what's happening with your values. But look at the axis. Remember how I said we started from 2 and we decreased first? So watch my polar axis. As I'm rotating my polar axis, you see how it's moving more and more towards the negative end of the axis? Okay, stick with me here. This is the positive end of the axis. This is the negative end. What happened at first on my graph is the graph first decreased towards its minimum. And so as I rotate, I'm going further and further down the negative end of the graph. And it's rotating, that's what gives it the curve. Until we get to this minimum. From the minimum, the graph is going to start increasing, which means on this axis, we're going to start moving towards the angle. From this point, I'm going to start moving more and more towards the angle. And so that's what happens. It continues, this point continues to move up the axis as the axis rotates. And it goes all the way until that point there. When I'm here, I'm as close to the angle as I'll ever be. And then the graph starts decreasing again. And so it starts moving further down the axis. It starts moving lower down it. That's how polar graphs work, okay? It's tricky. But once you get it, all of a sudden it'll just click and you're like, oh, I got a spinning axis and I'm either moving towards the angle or I'm moving away. And because it's spinning, it's going to curve. Okay, that's how it works. All right, I have one more here before we totally switch gears. Let's do one more. What do you notice about this rectangular graph? What can you tell me about it? Midline's 5. The amplitude is 2. So let's add the midline. I go up to 5. I have a midline. This graph is a cosine. It's a negative cosine. Does cosine start at its maximum, minimum, or midline? Maximum. Because of the transformation, it's actually going to start at its minimum. Go down 2 units. 1, 2, put a dot. And tell me about the period of cosine. What is cosine's period? So if I go all the way over to 2 pi, should have this point. All right, cosine's easier to figure out in my opinion, because if these are the 2 maximums, the minimum should occur perfectly in the middle. When does cosine attain its minimum? Pi. On this problem though, it's not a minimum, it's actually going to be a maximum. Maximum occurs at pi. The midline occurs perfectly in the middle of those two. When does cosine hit its minimum? Not minimum, I'm sorry, midline. Pi over 2 and 3 pi over 2. At pi over 2 and 3 pi over 2. When you're graphing an AP pre-cal, all you need is 5 key points. There they are. Connect those dots. And we'll use that graph to help us draw. Will this graph intersect the origin, which is called the pole on the polar graph? Will it or will it not?
No.
It never will. Why will it never hit the intersection?
It does not touch, but
This never touches the x-axis. So this will never actually hit the origin. We start with an angle of 0 at 3. So go 3 units to the right. Put that dot. The next key point. The graph, what's it going to do? Increase or decrease? Increase. So I'm going to move up this value up until pi over 2. What am I going to have at pi over 2? 5. So go up 5. 1, 2, 3, 4, 5. We should constantly be, I say constantly, I always say, I mean consistently be increasing. Consistently be increasing up until 5. So it just kind of curves outward like that. Out because the r, the distance from the origin, it's like your radius. The radius is constantly being increased up until that point. Now what happens? We go to pi and it continues to increase. It increases to what value? So by the time I get to pi, I should be out to 7. 1, 2, 3, 4, 5, 6, 7. I'm off, but I'm going to go ahead and put the point there. So my graph should continue to increase. My radius should continue to curve outward from the pole, from the origin. Now, after we get to pi, what happens? We decrease. We basically repeat, but now we are decreasing all the way around. Goodness, it's tripping on me. So we're going to decrease all the way around. I'll put the point at 3 pi over 2, which should be 5. 1, 2, 3, 4, 5. So just decrease and try to hit those points along the way. Tell me, does this look like a circle to you?
No.
It's not a circle. Does it look like a cardioid, a heart? No. It doesn't have the inner loop, does it? But they call it a convex limacon. I'm not sure what that means in French, but they call it a convex limacon. I have no special way of thinking about that one. A convex limacon is when it doesn't have the inner loop. It never hits the origin, but it's two separate numbers. Quick hits. What was the maximum value? 7. You got those from adding. And the minimum value you get from subtracting, 3. Let's take a look so you can see it better. Graphed over here. What was our equation? 5 minus 2?
Yeah.
Cosine theta. This is called a convex limacon. And let me start at 0 here. As you can see, we never hit the pole because this graph never intersects the x-axis. Okay? But this should be a lot more consistent of an increase and decrease than what I had before. But that's what it should look like. What do we call that again? Convex limacon. So a limacon is when your two numbers are different. If the two numbers are different, it's a limacon. If the two numbers are the same, it's a cardioid. What created the heart was the two numbers being the same. Limacons when the two numbers are different. All right? With that, we have a DOL. You can try this on your own. Let me ask this. Would this hit the x-axis?
Yeah.
Yes. This would hit the x-axis or the polar. But that you can do on your own some other time. And over here, you can summarize a lot of the things I've said. A cardioid is when A and B are equal. A looped limacon, or they call it a dimpled limacon. That's the same thing as convex. That happens when A is bigger than B. So anyways, you can figure that out later. Try DOL number 5. Now, as we move in to our example 3, I'm going to talk about symmetry a little bit. Symmetry with polar graphs. I used that word earlier. Symmetry means that like you could cut it in half and it's a mirror image on either side. There are 3 types of symmetry. I don't know if you remember, there were 3 types of symmetry. You could have symmetry with regard to the y-axis, symmetry with regard to the x-axis, and if it's not the y-axis, which means left to right, or x-axis, top to bottom, it would be diagonal. Do you remember what we called that?
The origin.
The origin. Symmetry with respect to the origin. Okay, so how does it play out with polar? Well, let me show you by using visuals. I'm going to use an x and y axis. I think it's just easier to see. Truthfully, I should be using circular graphs, but I'm going to show it to you this way. Visually, if a graph r theta, normally for r theta, where do we normally begin with theta?
The origin.
Not to the origin, sorry. We begin on a polar graph. I know that I drew x and y. We usually begin to which side? Up, down, on the circle. Where do you usually begin in a circle?
The right.
To the right. Usually we begin to the right and we move like a clock or against the clock? Against the clock, this way. That's what we normally do for a graph of r comma theta. That's normal. What this says, what if you had a value that produced the same values with this math? Okay, this is saying you have an r value. This says begin at pi, but move against the clock. Where is pi? The left. So we have the same r value. So whatever this distance is away, you begin the same spot. But this time I begin at pi. So if this one began at 0, this time I'm beginning at pi and I move against the clock. Let me do the opposite color. Let me do this in green. I begin here and I move against the clock. What type of symmetry is this? Is it symmetry with regard to the x-axis, y-axis, or the origin? This is the y-axis. If this case is true, you have symmetry with regard to the y-axis. And in polar terms, they don't call it symmetry with respect to the y-axis. They would give it by the theta. Y is the same thing as a theta of how much? Pi over 2. Theta equals pi over 2. Okay, that right there, both of these two cases mean the same thing. You could write it this way, r pi minus theta, or because that means you still have the same r value. That means the same distance away from the origin, same distance. Start at pi, move like a clock. Or this one says you start at the same location, but instead of moving up, you go down, and as you go down, your r is opposite, so you're straight across. So you start here, start across, go over there. So it's the same concept, negative r comma negative theta, and negative theta moves against the clock going this way, but since it's a negative r, it rotates it over. So it's actually the same exact graph. So same graph for both situations. All right, next one. Draw another graph. Let's get the standard. Normally, we begin on the right side and we move against the clock. Normally, we begin on the right side and we move against the clock like that. That's normal, r comma theta. Now this says you still have the same r value, which means the same distance away from the pole, but you move with the clock. So this one's saying move with the clock. So instead of starting there and moving that way, go this direction. This is when you have r comma negative theta, or that case, which I'm running out of space. It's the same thing. Negative r comma pi minus theta. Okay. For these, what type of symmetry is that? Symmetry with the x-axis or the y-axis? Or the origin? It's with the x. That's right. I'm going to go ahead and erase that. It's just too much going on. So symmetry with the x-axis in polar, what they call that, if you have symmetry with the x-axis, is they call that symmetry with respect to the polar axis. That's what they call the x-axis, is the polar axis. Finally, last type of symmetry, you could guess it from earlier this year. If it's not symmetry with the x-axis and not symmetry with the y-axis, but still symmetric, we'd say it's symmetric with the origin. This one's going to be with the origin. So you're going to start on the right, curve it up visually. That's r comma theta. What this is saying is you can start with the same theta, move this way, but instead of having a positive r, it's a negative r, which means it's across and going this direction. So this time, if it looks like this, if your symmetry is going like that, that means you are symmetric with the origin. The other way of writing this is starting at pi, but continuing to move against the clock. Both of those would give you that. That's symmetric with regard in respect to the origin there. So in polar, they don't call it an origin. Does anybody remember what they call it? I've said it a few times today. The pole. You won't have to write B twice. It says symmetric with respect to the pole. There you go. It says these three tests are sufficient to guarantee symmetry, but failing a test does not guarantee the graph does not appear symmetric. Sine. Sine is what letter again? Sine is y. Sine will always have respect to the y-axis, which in polar, what is another name for the y-axis in polar? Theta equals pi over 2. Perfect. And cosine. Cosine is what letter? X. Therefore, it would have, any cosine graph will have symmetry with the x-axis, also known as the polar axis. I'm running out of space. Polar axis. There we go. That's symmetry. All right, going through all that, what we're going to now do on example 3 is I'm going to show you some cool pictures. Now, these are harder to graph, so I'm actually not going to graph it here. I'm going to use the calculator. Let's go sketch this graph. Tell me what you know about the 6. What will the 6 tell us? Amplitude, which is the letter A. This time we have a letter on the inside. That is N. I want you to put here n is 5. What? Let's try this again. Put n is 5. And then let's go to the calculator and see what shape we see this time. It was 6 sine 5 theta. What does that graph look like to you? A flower. Perfect. Now, I want you to look at the x-axis, the rectangular graph. Look above the x-axis and below the x-axis. Is the graph basically the same exact shape one side as the other? Does it have the same maximum as this has minimum? Yeah. Because of that, this graph may complete itself in 1 pi. Let's check it out. I'm going to see when they're exactly the same above and below, they may repeat and it might only take 1 pi to repeat the whole graph. So I'm going to slide this around and let's find out. As I trace this, how long does it take? How many pi's? What amount of pi's does it take to complete the whole graph? It only took 1. And that's because this right here, they're perfectly matched up. Now, if I just change one number, I shifted this up 1. Does it perfectly match now? And now do I perfectly have the whole thing graphed in 1 whole pi? No. Now, as you can see, I have different size petals. The bigger petals would be for the higher maximums up here. The smaller petals would represent the negative minimums down there. These, if you count it, would only be 5 units, whereas these would be 7 units away from the pole. So that's what happens there. I'm going to delete that. So this completes itself in 1 whole pi. So come back over here. Let's fill this out. Actually, I am going to take a picture of that. Let's take a picture of that for our notes. This will be helpful to have. Oh my goodness. Not helping me out here. Must think I lost my eyesight, forgot my glasses or something. I don't know. It's trying to do this huge. Okay, I want to plot that on there. There we go. That's what the graph looks like. We call this a rose. It looks like a flower. They call this a rose. So go to your name. This is a rose. A rose occurs whenever you have a number greater than 1 with the theta. That's when we have a rose. The petals are very interesting. We said it can complete the graph in 1 pi. If the number is odd, you will be able to complete it in 1 pi. If the number was an even number in there, it would take all 2 pi and it would have twice as many petals. This has 5 petals, but truthfully, it does have 10 petals. Truthfully, it does have 10. It's just the second set of 5 are looped right on top of the first set of 5, if that makes sense. So technically, right here, there are 10 petals. It's just each one are doubled up. So it's like 2 petals right on top of each other. We only see 5, so they call it 5, but it's actually 10. Okay, where does this first maximum occur at? Let's take a guess. This first maximum right here, let me start this back over. We achieved the first maximum between pi over 12 and pi over 8. What do you think is between pi over 12 and pi over 8? Pi over 10. You're right. The first maximum occurs at pi over 10. Now, let me show you why it's pi over 10. Sine. Sine's maximum. Leave a little gap before you put the sine, or before you put the theta, because in a second we're writing a number. Sine's max occurs typically where? At pi over 2. Perfect. You knew that really well. Pi over 2. Now this problem does not just say sine. It had, ignore the 6 for a moment, or actually I'll put the 6. It had a 5 in there. That's the transformation. The transformation is the 5. Actually, I'll erase the 6 so we don't get confused on the 6. It has a 5. Now, inside, does inside lie or tell the truth? It lies. So instead of multiplying by 5, you divide. Because it's already a fraction, I think it's easier to divide this way, to write it as a reciprocal. And so what is pi times 1? Pi, and then what's 2 times 5? 10. Looky there. We got the exact same value we guessed from the graph. The first maximum occurs at pi over 10. Let's see if you could talk me through how you think you find the first minimum. Where does sine, leave a gap, normally have its first minimum? 3 pi over 2. Perfect. Put 3 pi over 2. Now this graph was not just sine by itself, it was sine with a 5 theta. What's that 5 actually doing? Is it multiplying or dividing? It's dividing. So if I divided it, what do we get there? 3 pi divided by 10. That's going to be the first minimum. By the way, the minimums and maximums will look the same on this graph, on the flowers, the roses. They look the same because it's just distance away from the pole. So the negative distance is the same distance as the positive distance, so they will look like the same type of petal. You won't be able to tell if it's a negative petal or a positive petal, but they're the same distance. Let me show you. So that was 1 pi over 10. When I come to this first minimum, it's right in here between 3 pi, 31 pi over 24. No, I'm looking in the wrong spot. It's in between 7 pi over 24 and pi over 3, which is 3 pi over 10. That's where that occurs. Somewhere in at 3 pi over 10 is right in there. That's when we get our first minimum. Okay, so the maximums and minimums, how often do they repeat? Well, here's what you need to ask. How far apart are these values? What you would do to find out how often they repeat is you would say, well, it's 3 pi over 10 minus pi over 10. And what do you get?
3.
No, not 3. 2 pi over 10. And 2 pi over 10 can reduce to become pi over 5. So the maximums and minimums repeat every pi over 5. I took away, I subtracted these two values and simplified. That's to figure out how often they repeat. Okay, take a look at the graph. What type of symmetry does this have? Is it symmetry with the x-axis, the y-axis, or the origin? Nope, nope, nope.
None.
Origin's if it's perfectly diagonal. That would mean if you drew a perfect line, I'll show you why it's not, here's the origin. If it was origin, if you took this one and you went straight through the pole, you should have a point straight across. Do I have a petal straight over here? So it's not the pole, it's the y-axis. And now in polar, we got to get the name right. What's the name of the, did I say polar axis? What's the name of the y-axis in polar? Theta equals pi over 2. That's what it's symmetric with. All right, I have a part B. Let's try this one out. This time I have 8 cosine 2 theta. What is my n value on this one? 2. What we're going to learn is that if your n is even, you double the number of petals. They will not overlap. So how many petals will this have? 4. 8 cosine 2 theta. Do I complete the graph at pi? If I move this to pi, have I completed the whole graph? No. How long will it take to repeat this whole, or to complete the whole graph? It'll take 2 pi, that's right. It takes 2 pi to complete this whole graph because it was an even number. Even numbers, the way the math works, even numbers, it takes a full 2 pi. Even n values, I should say. It takes a 2 pi. Odd will only take 1 pi. And that's just because mathematically, when you do the calculations I did earlier, when they would overlap and when they don't. It's just the math, how it works out. Even versus odd. Okay, there's our graph. So the first maximum, where does the first maximum appear to occur? Right here. What angle would that be? What theta would that be? 0. It's going to occur at 0. Here's why. When does cosine leave a gap before you do the theta? When does cosine reach its max typically on the unit circle? At 0. Let me put theta equals 0. Now this one is not just cosine theta, it's cosine 2 theta. Is that 2 actually multiplying? What's it doing instead? Dividing. If you divide that by 2, what is 0 divided by 2? 0. So that's why its first maximum is at 0. Now let's talk about cosine's minimum. Typically, typically the cosine's minimum occurs at pi. Very good. It typically occurs at pi. Now, this is not just a normal cosine, it's cosine 2 theta. What is that 2 actually doing? Dividing by 2. So its first minimum occurs at pi over 2. So when you look at this graph, this pedal right here at 0 is positive. This pedal at pi over 2 is actually the negative. That's the negative pedal because it's the minimum. It's the minimum. It's when cosine's negative, believe it or not. Okay, and I could show you that if you wanted to see it. How often do they repeat? Well, you'd subtract one from the other. What is pi over 2 minus 0? Pi over 2. They repeat every pi over 2. That was easy math. That's nice. Symmetry. What type of symmetry does this graph have? Does it have symmetry with the x-axis? Does it have symmetry with the y-axis? Okay, let's talk about the origin. I want to pick a point. How about pi over 6? If I go across pi over 6, do I have another point the same distance away? And if I started to rotate this way, if it won't let me spin this one. But if I started to rotate it around this way, would it be coming closer over here as well?
Yes.
Yeah, so guess what it has?
Oh.
It has all three symmetries. This is called a, what do we call this graph? Looks like a flower. We call it a rose. And this has symmetry, all three symmetries. So this has y-axis, x-axis. It was a cosine, so it was for sure going to have x-axis. And origin. It has all three. What are the polar names for those? Do you remember? Theta equals pi over 2. Good. What about the x-axis? What do we call that one? This one's called the polar axis. And finally, the origin we call the pole. Good. All right. We have an extra practice you can look at and try on your own. But how about we go to DOL number 1? DOL number 1. All right, example 4. This is my favorite. Example 4. We're going to decide if the graph takes 2 pi or 1 pi to complete the full shape. Are you ready? Watch mine. How you would do this on a test is you would use your pencil and spin it. Tell me, when I spin this, can you trace the whole graph with this by the time we make it to 1 pi, or do we have to go all the way around to get the whole graph? So I'm going to trace it, and as I trace this, notice the point is right here, right now. How far do I have to go around to trace the whole shape? At 1 pi, have I traced the whole shape? No, I'm starting on the positive end of the graph. I'm decreasing, decreasing, decreasing. I'm at here, this point now. Have I completed the whole shape though? No, because now I'm going to start going this way. It takes how long? It takes 2 pi. This one requires 2 pi. All right, how about this next graph? I'm starting to trace it here. I'm tracing. We're tracing this first flower right there as I spin it. Okay, now I'm completing my first flower petal. Now where am I going? Am I just graphing the middle of nowhere? No, now I'm graphing this petal. I get to there, and now I'm going to pick up with this third petal. After I complete the third petal, now which one's my fourth petal? This one down here. I've got it done, and now I'm going my fifth petal. I complete my fifth petal. How far have I gone? Look, the plus is on the left. That means it requires 1 pi. I'll put the 1 in there. It only requires 1 pi. Odd number petals only takes 1 pi. Even takes 2 pi. All right, how about C? How many petals do you see? 8. So how long will it take? This will require 2 pi. Again, you could spin your axis to try to trace it. All right, a circle. Think of a circle much like a flower. How many petals would this be? 1. Would that be 2 pi's or 1 pi needed if it was an odd number? 1. It only requires 1 pi. Circles only require 1 pi. You have some extra practice. And now take a look at DOL number 6. DOL number 6. All right, example 5. It says find the points of intersection for the graphs of r equals 1 minus 2 cosine theta and r equals 1. State the solutions at any common points. Use the graphs to determine common points. Well, I can look for the intersections first. So here's the equation r equals 1. It's right here. And, just to help you see it better, I can do that one in red. So we have 2 different colors. We can do that. So that's the graph of r equals 1. And then here, the 1 minus 2 cosine theta, that's a looped limesome. And you can see there's 3 different intersections. There's this intersection here, here, and there. Now, what you would need to think about is on a rotated axis, where these intersect. 2 of the values are going to be quite simple to find, but one of them might be a little bit trickier for us. And so I'm going to do this this rotated axis. Let me give it a different color. How about blue? As I spin this around, what you'll notice is this graph intersects first straight up at the top, which would be up here at pi over 2. We have an intersection at pi over 2. Now remember, the graph can only exist at one spot, at one point at any one location. So if that's pi over 2, then this one would be when I loop all the way around, and that will be at 3 pi over 2. And those will be those 2 locations. But this one's a little bit tricky because it could occur at 0 on this line. See, notice we're intersecting. Or it could be when we're at pi, or that could be there. Now, because of this equation, I want you to think through, when is it -1? When does that intersection happen? Well, it's -1 whenever cosine itself is 1. When does that value, that's a r value of 1. How do I get a 1 or a -1? It's when I plug in a 0. Cosine and 0 is its maximum, so it'd be 1 there. -2 times 1 is -2. 1 minus 2 is -1. That point occurs, let me take that off. This point occurs at the r value, or excuse me, the theta value. Let me say this is a r value of -1 when theta is 0. That's the location of that point. And this point here, that's when we have a pi value, and that's 1, 2, 3. That's a +3 when we're at pi because we're going towards pi. Now, how did I know that? Based off this graph. To get to its maximum, I got to be left. The maximum would be 3 when cosine is pi. And this value must be when we're the farthest to the right, but it's just a -1. That's what makes it go back to the left. This point right here would be at pi over 2. So that has a r value of 1 when we are at pi over 2. Oops, pi divided by 2. And then this point here, yeah, okay, just making sure in my head, that is when we're at 3 pi over 2. Yes, because that would produce zeros for the cosine, and so 0 times -2 is 0, and that would be 1. Yeah, that's right. So those are the locations. So where do we actually intersect the 2? We would intersect the solutions here. The solutions would be when theta equals pi over 2. Well, 0, I skipped that one. At 0, pi over 2, and 3 pi over 2. On the interval going from 0 to 2 pi. That's when we would have solutions, and the solutions would be these intersections. These would be my three intersections. Here's solution one, sorry, I'm out of order here. That would be solution two, technically. First solution would be here when theta is 0, and this would be my third solution there. Okay, so let's try this again. Now, once again, as I examine this graph, I see that there are three places of intersection. We have an intersection here, here, and there. Now remember, you start on the right, so this graph would start here, and as we move around this intersection, it looks like this one would be at pi over 6. That here is at pi over 6. The next intersection occurs when we're at this pi over 6. It's almost 1 whole pi. So if that's 0, this is almost 1 whole pi. That means it's 5 pi over 6. And then this would come around when we're at 3 pi over 2. So the points of solution, the solution sets, I could list out the points here. It's theta equals pi over 6, 5 pi over 6, and 3 pi over 2 on the interval from 0 to 2 pi. And the values there, it looks like this point here has an R value of 0. This has an R value of maybe 1.5. Let's see here. If at pi over 6, I'm doing my hand trick here. Sine would be 1/2. That would be 1.5. This would be at 1.5, comma, pi over 6. Because sine is 1/2, you add that to 1. And then over here would be the same thing. That would also be 1.5 at 5 pi over 6. So these would be my three solutions in order. I have them written 1, 2, and 3. Those would be my solutions there. Now go try DOL number 3. DOL number 3. All right, as we conclude this lesson, I'm about to show you a topic that I don't believe is tested, but still goes with polar graphs. Is this: how would you transfer or convert from one type of function from polar to rectangular or rectangular to polar? Well, you would use these same formulas that we used last class. So I put this slide here just to help you recall how to do so. If you wanted to switch between polar and rectangular equations, this right here is rectangular. What you would do to convert is you can, if you want, remember that y is r sine, x is r cosine. You could also, if you are dealing with multiple squareds, use this formula here. What I'm going to do is I'm going to say this is equivalent to r sine. Y is equivalent to r sine, which means x squared is the same thing as r cosine squared. And how you would solve this is you would have to isolate the r value. So it would be r sine theta equals 1/2 r squared cosine squared theta. And I'm going to get my r's of the same side of the equation so I can do a GCF or factor, or excuse me, I have a squared over here. So what I would need to do, the simple way of thinking about this would be divide out an r. The truth be told, we're going to have issues if r equals 1, but I could still think about solving this equation since those are multiplying, dividing by r. There's just a problem where if r is 0, we have an issue there doing this. But now I have that sine theta equals 1/2 r cosine squared theta. What I could do is multiply both sides by 2. That gets rid of the 1/2. So 2 sine theta equals r cosine squared theta. And finally, you would divide by your cosine squared. And to clean that up a little bit, if you use your identities, I'll write it this way. This is the same thing as 2 sine theta, and then divided by cosine theta this way. Whoops, how about this? Cosine times cosine. And I'm just going to put a times 1 there. If you remember that this it represents a tangent, sine divided by cosine is tangent. Got the division sign. And this right here, that right there becomes a tangent, so it's r equals 2 tangent theta. And this is the same thing as secant. Right here, this right here, 1 divided by cosine is secant. So it'd be 2 tangent theta secant theta. That should be my answer here. And you can check these on the graph, but that's how you would go about this process. Let me just get a brand new graphing calculator and I'll show you. If I looked at the graph, y equals 1/2 x squared, y equals 1/2 x squared, and then I graphed r equals 2 tangent theta secant theta, and I think on Desmos you have to do a multiplication symbol. Let's see here, multiply and multiply. What is it not doing? What does it say? Put parentheses around the thetas, it says. There we go. And as you can see, the two graphs look 100% the same. So we did do that correctly. If we tried part B, I would use the same substitutions. So this would be 4 times r cosine squared times r sine equals 1. Immediately, I could divide each side by 4 after substituting out the x and the y for r cosine and r sine. So when I do that, I'm left with r squared cosine theta times r sine theta equals 1/4. If I combine my like terms, I now have r cubed cosine theta times sine theta equals 1/4. And now what I'll do is from both sides, I'm going to divide out that cosine and sine. And so I'm going to write it over here, dividing out the cosine times the sine. So I'll put it over 1 like that. And so when I do this, I'm left with r cubed equals 1/4 and cosine theta sine theta, and I'm going to rewrite it one more time. When you have denominator cosine and sine in the denominator, that's the same thing as secant and cosecant. So I could say that r cubed equals 1/4 secant theta times cosecant theta. That could be your answer, or if you wanted to cube root it. If I cube root each side, this would cancel over here, and r would equal the third root of 1/4 secant theta cosecant theta, and that would be my answer there. Again, we could go graph these and check it out. 4x squared, y equals 1, and then the next equation, r equals, I had the third root. Let's see here, where's the third root? Functions. There it is. Third root of 1/4 secant. I had to put a parentheses around the theta this time. I'll remember that. Cosecant theta. And we have some mistake here. I need to go back and see where I messed up, but somewhere in there it did not quite work its way out right. I'm not sure where I went wrong, but I'll have to check that out. Nope, I see my mistake over here. The cosine should have been squared. So all this way, that cosine needed to be squared, which means this cosine is squared, and when I divide, I'd be dividing by cosine squared. So this is cosine squared, this is a cosine squared. This becomes a secant squared, and so finally this is a secant squared. Let's see if that fixes it. So if I put it in here, secant squared, yeah, there we go. That's what we needed, and that would become my equation. Example 6c here, as I continue on, if you're working with the r by itself, the easiest way to get around this is if you square both sides of your equation. If you square both, you get r squared equals 4 squared. And r squared is equivalent to x squared plus y squared. And 4 squared is 16. That would be our solution this time around. And I can show you that. So we have r equals 4, and then x squared plus y squared equals 4. That's in not 4, 16 now. And notice those two graphs are exactly the same. So we got that one right. Okay, now theta, what could you do with that? If you're left with the theta, this is where you use your tangent. You take the tangent of both sides. So tangent theta would equal the tangent of 2 pi over 3. And tangent of theta, sine is y, cos is x, tangent is y over x. We could substitute and say that's y over x equals tangent 2 pi over 3. That if you use your hand trick, you bend. 2 pi over 3, by the way, is in the second quadrant, just as a reminder. 2 pi over 3 is in the second quadrant, which means tangent would have a negative slope. This is going to be a negative value. 2 pi over 3 is here in the second quadrant. So it will be a negative tangent value. I bend my index finger. I flip my hand for the pi over 3. I have square root of 3 for y's, and my x would be negative square root 1. That could simplify to be the square root of 3 over negative 1, which is equal to the negative square root of 3. If that's the case, to finish this off, y over x equals the negative square root of 3. All you have to do is multiply both sides by x, and you have your equation. And this will be that y equals negative, square root of 3x. As I mentioned, tangent is the slope. It was a negative slope. That's the negative slope right there, negative square root of 3. I don't think Desmos will graph theta equals 2 pi over 3. You should know that one though. But I will graph y equals negative square root 3x. Notice that would go right through where 2 pi over 3 is located right there. That should be where the 2 pi over 3 is located. Two more. R equals 6 cosine. On this one, I would do this a little differently. I would multiply both sides by r. If I multiply both sides by r, let me write it out like this. R times r equals, how about r times 6 cosine theta? The reason I would write it this way is this is r squared. This becomes 6r cosine theta. R squared, if you remember, is the same thing as x squared plus y squared. That's Pythagorean theorem. And r cosine is x. So you could leave it in this form. A lot of times what we actually do in math is we would subtract over the 6x and we would complete the square. So when I do this, when I subtract that over, I would have x squared minus 6x plus y squared equals now 0. And what many mathematicians do is they complete the square. If you remember this process, you take your b value, you divide it by 2. So negative 6 gets divided by 2, which equals negative 3. And then what you do is you take that value and you square it as you go back in. Negative 3 squared is plus 9. If I add 9 on the left, I need to add 9 on the right. This right here will simplify to be x minus 3. It's this number right there, x minus 3 is quantity squared plus y squared equals 0 plus 9 is 9. That's going to be the equation here in rectangular form. And if I graph these two, they should be one and the same. We knew this is a circle, if you remember from earlier today. So r equals 6 cosine theta. And we just came up with, whoops, what in the world? Let's try this again. X minus 3 quantity squared plus y squared equals 9. Notice that's the exact same circle. So we did that right. All right, I have one more. This is basically kind of doing the opposite of what I did a moment ago. Here, what you would have to do is you'd have to FOIL out this math. You'd have to expand it. So here, if you're squared, it'd be x times x. First times first, then the x would multiply times the negative 3 in the second parentheses. Let me just write it out twice so you can see what I'm talking about. This would be x minus 3 times x minus 3 plus y minus 2 times y minus 2 equals 13. And so when I multiply this, I would have x squared. I'm FOILing or distributing. I'd have a negative 3x, a negative 3x, and a positive 9. Over here, I would have a y squared that's being added, positive y squared, a negative 2y, another negative 2y, and finally, I'd have a positive 4 equals to 13. First thing I would do in simplifying this is I would combine some like terms together. Here I can see that I'll definitely have a negative 6x, I'll have a negative 4x. This 9 plus this 4 is going to be 13. I'm going to actually, as I do this, I'll just subtract 9, I'll subtract 4, which means I'm subtracting 13 from both sides. Subtracting 9 and subtracting 4 is subtracting 13. All of these simplify out of there. I'm left with x squared minus 6x plus y squared minus 4y equals 0. And I'm going to group my x and y, x squared and my y squared together. And then I'm going to have a negative 6x and negative 4y after equals 0. And now I'll substitute. X squared plus y squared is r squared minus x is the same thing as r cosine. And y is the same thing as r sine theta. Here, what you could do to try to simplify this, if you wanted to, you could factor out an r from here and say this is r. If I factored out the r, you'd be left with r minus 6 cos minus 4 sine. If you wanted to write it that way, you could. I don't know which way would be more proper on this one. You could leave. I'm going to leave it like this, but this equation would be the same exact thing. If you want to try one, by all means, go for it. But either way, try DOL number 2 on the back of the packet. DOL number 2. Now, once you've completed DOL number 2, make sure you submit everything in online.